This result is called Kolmogorov Chapman equation. Okay. I won't write this formal result. I'll leave it as an exercise. It's easy, straightforward. Okay. So now you know, right? If you start at state I and if you want to go to state j in n steps, that is n time slots, that probability is nothing but you take the probability transition matrix, raise it to the power n, look at the ijth entry, that will give you the probability. Is that fine?
Yes, sir.
Okay. Now, let's look at a few other things. Okay, so now from this we know that I can write these states as circles, right? We saw that here, right? We can write these states as circles and transition probability as some basically the entire Markov chain can be encoded as a graph, right? With the node being states and edges being, in fact, it's a directed edge being, it's a directed graph, and the weights being the probability. Is that okay? Is that fine, everyone?
Yes, sir.
Okay. Now with this, we'll look at a few definitions. Okay. Let's look at a few definitions with this encoding. Okay. Okay. So first thing is n step walk. How many of you are familiar with the graph theory, elementary graph theory? Yes, sir. No, you just have to answer. No.
No, sir.
Okay, fine. No problem. So what is an instant? So I'm considering Markov chain encoded as a graph, okay, directed graph. You can imagine what the picture, right? So what is a walk? Basically, you go from one state to the other, right? That is a walk, right? In fact, it's an ordered walk. Ordered string of nodes. Okay. So for example, I0, I1, and so on, n greater than or equal to 1. That means I start at state I0, immediately I go to state I1, and so on. After n steps, I go to state n. Okay. Such that, well, there should be an arc from I0 to I1 and I1 to I2 minus 1. What does that mean? That means that the probability of you going from I0 to I1 in one step should be non-zero. Probability that you're going from I1 to I2 should be non-zero, and so on, right? That's what it means, right? Probability of you going from im minus 1 to im is non-zero. If there is no, if this probability is 0, there is no arc between the two states, right? There is the arc would be vacuous because the weight will be 0. Okay. So what does this mean? So for example, if you have let's say I take this thing, okay, 2 is a state 3. This is a typical walk, right? I go from 0 to 1, 1 to 2, 2 to 3, and so on. And this, okay, now I'll write the typical walk. So you go from 1 to 0 to 1, 1 to 2, 2 to 3, 3 to 1. Okay, this is a walk. Note that I've started at 0, went to 3 and came back to 1. So I have entered the state 1 twice. Okay, but still it's a walk. Okay, is that fine?
Yes, sir.
Okay. Now the second thing is what is known as a path. Okay.
Sorry, sir, I missed the point.
See, you start at 0, went to 1, 2, 3, and back to 1. That's a path, right? And you could have, for example, if there is a path like this, I mean, if there is a link, then I can even go back to 0 also. That's also a path. Or I can go from 0 to 1 to 2. That's also a path. So essentially, all possible traversing. Okay,
That
you take
means
any traverse. That's a path.
in a
That's
path
a walk.
Cross a node more than one times.
Yes, yes, that's a walk.
Okay.
Okay. There is something known as a path. Okay. So path is a walk with no cycles. Okay. Walk without entering the same node again. Okay. Without or entering a node twice. Node twice or more. Or it's a walk. I'll just simplify this. Okay. Basically, it's a walk in which no nodes are repeated. Okay. This is the path. Okay. So clear, right? You cannot circle. You cannot come back to some state. Okay. There is something known as a cycle. What is a cycle? Hmm? Again, it's a walk in which the last and first node are the same, and in between no nodes are repeated. Okay. Walk with first and last nodes being same, while no nodes repeated in between. Okay. Is this fine? Cycle is like
Yes,
this.
sir.
This no repetitions. Okay. There are nodes in between like this. Okay. Path is no repetition. It's a walk, but there is no repetition of any node. At least you start here and come back here. At least this node is repeated in cycle. Only this node is repeated. Okay, that's a cycle. Walk is arbitrary. Okay, path is without cycle. Okay, fine. Okay, now with this we'll look at a few definitions. So now I have encoded everything into a graph, right? The entire Markov chain. Okay, we say that a state J is accessible, okay, from I, denoted. So basically, state I can go to state J. Okay, that's what it means. State I can go to state J. This is with the notation. Okay, if there is a path, right, or a walk, there is a walk from I to J. What does this mean? Any idea? If there is a walk from I to J, what does that mean? I can start at I, that means the probability that I start at I, go to J, in some step, let's say L is greater than 0 for some L. Okay. Then we say that state J is accessible from state I. Is that fine?
Yes, sir.
Okay. Now, okay, I'll write one more thing and distinguish the two. Okay. Suppose you have two states. Okay. There's some, I don't know. I think maybe I have to change. Oh, what happened? Oh my God. Okay, so I'll sorry about this. So I'll continue with whatever I was discussing. So okay, so now we say that I communicates with J if, of course, denoted I j if I communicates with I can talk to j and j can talk to I. Okay, is this fine? Okay, is this fine, everyone?
Yes, sir.
Clear? Huh? Okay, yeah. So now let's see what is this. So if you have a state, right, with let's say some states, and you have a Markov chain with certain states, finite states. With this notation, right, communication, let's say I and j communicates this notation, this will split the entire chain into a group of states. Let's see what does that mean. Okay, let's see first of all. uh, okay, so let's look at properties of this. Okay,
Hello,
I,
sir.
yes.
Sir, I and J are accessible. I mean, the first notation, I right arrow to J. Sir,
Hmm.
doesn't that imply J can also come to I?
No, not necessarily, right? Not necessarily. See, in the first example itself, from 3 you can go to -3, but from -3 you cannot go to, you can, okay, in that case, but I can give you an
Oh,
example. Okay, so we will see. Maybe I'll give an example and then start the property. Is that
okay,
fine? Okay,
okay.
I'll just give an example. 0, 1. Okay, so it goes here with probability P, here with probability P. Okay, it comes here, or stays back with probability 1 minus P, 2 with probability 1. Now what will happen? See, from 1 it can either, sorry, what is this? No, sorry, this is what, if it goes out with probability P, it can go over here with probability 1 minus P and 1. What can you say about this? See, from 1 to 2 there is a non-zero probability. If I am in state 1, there is some non-zero probability that I can go to state 2. But there is no return from state 2, right? The moment I reach state 2, I cannot come to 1. So 1 to 2 there is a communication, but there is a path, but from 2 to 1 there is no path, right? Is this fine?
Yes, sir.
Huh?
Yes.
Well, 2 is called absorbing state, so because the moment you go to 2, you'll stay there forever. Okay.
Okay, sir.
Okay, so I communicates with I. Why? Clear, right? So because Pii in 0 is 1, which is greater than 0, right? That's the definition, right? So I communicates with j, that means Pij, right? I communicates with j means what? You start at I and you go to j, right? Pij. So Pij of n is greater than 0. That means in n step for some, or L, in L step, you can go from I to j with non-zero probability, right? But I communicates with I because Pii of 0 is 1, because you're already there. Fine. Okay. I communicates with j implies j communicates with I. Trivial, right? Why is this trivial? By definition, right? Pij,
Yes.
yeah, so it commutes. See, if I communicates with j and j communicates with k, implies I communicates with k. How do you prove this? So what does this mean? This means that there is a path from I to j. That means with non-zero probability after some steps k. So let me write this. This is the proof, right? So Pi to j in L step is non-zero. Pj to I in some M step is non-zero. Okay, that's what this means. What does this mean? This means Pj to k in N step is non-zero, and k to j in just give me k step is non-zero. Okay, is that fine? So if what is it that I have to prove here? First thing that I have to prove is Pik in some step is non-zero, right? So I have to say this is non-zero. I mean, it's greater than 0. So what do you mean by that? So I can write, so clearly I can go from I to j in L step and j to k in n step. So I to k in L plus n step, right? At least. Do you agree? Hmm?
Yes, sir.
Okay. So that means I can go from I to k in L plus n step. What is this? This is, I can write this as what? Summation Pi to j in L step, P j to k in n step. Okay. What should I sum over? I should sum over all j, right? All possible j in between, right? Well, just to avoid the confusion in notation, this j can be, give me some other variable. No, let me call it as o. Okay, o is some state, in between state. Okay, o. But definitely I'm summing over all state o, but one of them is j, right? Do you agree? There will be something like oj in L step, jk in n step. Do you agree? This will be one of the terms in this summation. Do you agree?
Yes, sir.
So this will be greater than this. Do you agree?
Yes, sir.
So that will be greater than 0. Because why? Because of this and this. This will be greater. So that means Pik in L plus n step is greater than 0. So you interchange the role of I and k, you will get Pki in some steps will be 0, greater than 0, right? Same proof. Do you agree?
Yes, sir.
Is that
Sir, is
fine?
it hello, sir?
Yes.
Sir, is it possible that I go from I to J in L step and J
Hmm.
to K in N step, but
Hmm.
maybe when I go from I to K, there will be
Hmm.
some O, I mean some intermediate path that
Exactly. Yeah, you can probably go in one step also. You never know.
yeah, yeah.
Yeah. But what I'm saying is there is some number of steps using which you can take so many number of steps, some finite number of steps, and reach that state. That's all I'm trying to say. Okay. I'm not saying lesser number of steps is impossible. No, you can in fact go to the other state in one step only. We don't know. Is that fine?
Yes, sir, yes, sir.
Okay. So, Sumit, can you tell me what can you infer from this? I communicates with I communicates with J, and J communicates with I. I communicates with J, and J communicates with K implies I communicates with K. What is this called?
It's a relation, no sir.
What
Equivalence relation.
exactly, right?
Yes,
So,
sir.
okay, those who don't know this communication, whatever this notation brings in an equivalence relation among the states. Okay, why is it called equivalence? So for example, a is equal to a, right? If a equal to b, then b equal to a, right? If a equal to b and b equal to c implies a equal to c. So it satisfies or mimics this equality, but it's not really equal to. So it's called an equivalence relation. This is called equal to relation. This is in general called equivalence relation. Okay. So what is the impact of what is so the moment I say there is an equivalence relation, so this implies
Dual
this,
partition.
yes, this is an equivalence relation on S, the set of states. So what does that imply?
It will
This,
partition the S.
yes, right? Partitions, yes, right? Into what?
Equivalence classes.
Yeah, equivalence classes. Within those classes, the nodes can communicate with each other. Outside the classes, it cannot. So let me give you an example. So 0, 1, it can communicate. Okay, so it goes back and forth. And there is 2, 3, it can go back and forth. Okay, now there can be communication across. Okay, so maybe there is, okay, so with let me write this. So this goes with probability p 1 minus p. This comes here with probability p, or goes here with probability 1 minus p. This is p and 1 minus p. So yeah, this is again p. What kind of a Markov chain is this? See, the moment you go to this state, right? For example, this chain here, the entire is one Markov chain. But the moment you enter into one of these states, that's it, right? You cannot come back. You will be stuck in 2, 3. But you'll go back and forth from 2 to 3. So 2 communicates with 3. So this forms an equivalence relation class. 0 communicates with 1. So this forms an equivalent class. But the moment you go out, you are done, right? It partitions into 2 classes. Is that fine? Do you agree?
So that
Because
means
Yes, sir.
0 doesn't communicate with 2, right? Because the moment you go from 0 to 2, yes, there is a probability 1 minus p, but you cannot come from 2 to 0. So 0 and 2 does not communicate with each other. Yes?
so that means there will be equivalence relation within classes in S.
Yes, so I can say whether, if you give me 2 classes, I can say whether it communicates with each other or not. That will sort of, I can group them, right? All the states which communicate with each other, I can group it into one basket, right? Oftentimes what happens is all the states will be in that one basket. There will be no other states left over. But in this case, what happens is in one basket I have 0, 1 because 0, 1 communicates with each other. There is another basket 2, 2, 3 which communicates with each other. So there are 2 baskets, right? So equivalence relation is sort of partitioning it into 2 baskets.
Hello, sir.
Yes.
So was it necessary for a connection from 0 to 2 to be called the
Well,
equivalence?
yeah, I mean, if you remove this, right, connection, then it's too trivial, right? You are taking 2 different Markov chains. Why do you want to consider it as one? Of course, you can do that if you are okay. So this is very trivial, right? This is a, now what can you say? So 0, 1, this is one Markov chain, this is another Markov chain, right? Of course, you can combine them and say, well, transition from 0 to 2 is happens with probability 0. That's as good as taking 2 different Markov chains, right? Do you agree?
Yes, sir. So I mean,
Yeah.
sir, the notion of equivalence comes.
Exactly. So you are right. If I consider 0, 1, 2, 3 as one state, if you consider these two as one Markov chain, equivalence relation will split it into 2. 0, 1 will fall in one basket, 2, 3 will fall in another basket. In this case, those two are different Markov chains altogether. You can treat it as different Markov chains. But the moment I put this, right, 1 minus p, I cannot say that these two are different Markov chains. They belongs to the same Markov chain. But different, I can split this into 2 different equivalence classes. Okay,
Okay.
is that fine?
Yes,
Yeah.
sir.
Okay, so we will continue with this in the next. Okay, so I think the big picture wise, what is it that we are trying to do? Maybe I'll describe this in the next class. Okay, so I probably should have done this before doing this equivalence. Okay, just read what is equivalence relation and try to see why it partitions the set into disjoint subsets. Okay, just read through that, but otherwise this is what it is. Generally, the big question that we are asking is whether there is a stationary, what is known as stationary distribution for a Markov chain. That is the big question that we are asking. Okay, it has its own advantages. We'll see what are those advantages. Is that fine? Okay.
Yeah, okay, sir.
Okay. So I'll stop here. In the next class, we will continue with this Markov chain further. And then this time, I thought I'll also teach a little bit of Markov decision process (MDP). Okay, which is a part of this, and luckily that's there in the book as well. I mean, it's a part of this chapter, so I'll do that as well, so that you know what MDP is. Okay.
Okay, sir.
Okay.
Okay.
Yeah. Is that fine, Ayush?
Yes, sir.
Okay. Praveen? So
Yes, sir.
remember, we'll have a quiz next week. So start preparing. Okay.
Okay, sir. Okay.
Okay. So
Okay, thank you, sir.
yeah. Thanks and happy Deepavali. So
Thank you too,
we
sir.
will
Happy Diwali, sir.
yeah. Thank you. We will meet